Hello, this is my lane detection algorithm for remote sensing with Dr. Mitchell. Here we're applying the algorithm to the first test video. So during class, we set up the initial part of this algorithm to go from the original image all the way to getting predicted lines with the Hoff transform. So for this assignment, I'm taking these lines and I am drawing predicted lines onto the original image. So how I'm doing this is I am taking these lines and trying to decide which ones are right lines and which ones are left lines. So from the Hoff transform will return a positive row value for lines that pass below the origin, such as the left line, and it will return negative row values for lines that pass above the origin. Just how we're snipping this video, we're placing the origin in such a way that this is possible to make a distinction between those lines. So once we have the two groups separated, I'm averaging the row and theta values that the Hoff transform are returning to find an average distance from the origin and angle for each of the left and right lane lines. And once I have an average predicted line for the left and right side for each frame, I'm going to take a moving average between frames. So to reduce noise and to create a smoother predicted line. So this is extremely useful for these dashed lines where there's less information between each dash. So you can see that there's less detected lines between each dash. So taking that moving average between frames will help bridge that gap. The size of the kernel that I used is fairly small, so you can see that there is still some movement of the line. So if I used a larger kernel size, I could get that line to be more steady, but then I would lose responsiveness from the algorithm during a turn or if the car is to shift in the lane. So I can play the second test video. So the second test video, the main difference is the brightness of the video. So you can see that it is taken during the daytime. So the main thing that this affects is the value that I have to use for the threshold. I just manually found a value that worked. And I'm adjusting that based on what video is playing. This could be improved by dynamically sensing the brightness of the frame and picking a value based on reasonable threshold conditions that have worked in the past. Additionally, you can see when this video starts, there's a bright flash as the camera turns on and is adjusting to the lighting conditions. I'm combating this by just delaying the algorithm for a second or two as the camera adjusts to the light. So you can see that once the camera gets saturated, there's a flash of light and my algorithm performs fairly poorly just because it can't tell the difference between the lane and the road. So I'm just delaying the start of the algorithm. Additionally, I'm trying to bound the lines between a certain range. So I'm assuming that we're driving parallel to the lines and not cross lane lines. So I'm rejecting any horizontal lines, which is helpful for any stray lines that might creep through the algorithm or any additional lines on the side of the road. So you can see in the masked image that I am picking up those right lines between the lanes, which will give a lot of horizontal lines. So I'm able to just reject those and not let them affect the lane prediction. This obviously, again, reduces robustness, but increases performance. So I think the assumption that we're driving parallel to the lines is a fairly safe one. This algorithm could be improved by projecting the line from one line to the other. So we know the standard distance between the lines. So if we are able to confidently measure one of the lines and not the other, then we could try to project from one line to the other. This could help during situations where one of the lines drops away, such as during merging areas.